Have you ever wondered why some objects float and some don't? Well, the answer for that is when an object is partially or fully submerged in a medium, there's a force exerted on that object opposite in direction to its weight called the upthrust. So, how does it arise and what are the effects of it? Let me explain.
So we are going to use an appropriate coordinate system to solve our problem. We are going to use the good old Cartesian coordinate system, but we're going to assume that the origin lies on the top of the medium, and also the z-axis is pointed in the downwards direction. When we pick that as our coordinate system, the value of g, which is the gravitational acceleration, is negative 9.8, and the depth is simply the z component. Thus, the gravitational pressure equals z rho g.
First up, we know that there's a pressure created inside of the medium due to the force of gravity. And this pressure is going to act on the surface of our object and going to create a net force. And this net force is what we call upthrust. We know that the pressure due to gravity is equal to h rho g, where h is the depth and rho is the density of the liquid and g is our good old gravitational acceleration. Now, to further simplify our problem, we're going to break up the surface of our object into tiny differential surfaces. The idea behind doing this is that now we can calculate the force exerted by a single differential surface and add all of those forces up and obtain an answer for the net force. And now we can work out the force exerted by one of these small surfaces without much trouble. What we all have to do is multiply the pressure at that particular point by the vector ds. Now what we all got to do is just integrate this thing over this surface S. So to further simplify this expression, we're going to use the Gauss's divergence theorem. But first, we got to do a slight modification to this theorem. What we're going to do is we're going to dot both sides of the relation by some constant vector, which means that this vector does not vary no matter which parameter varies. And as we know, vectors have the distributive property, so we can take this vector inside of the integrand. On both sides, there is a vector dot with a vector, and that whole thing is dot with another vector, and a vector dot with a vector gives you a scalar, and a scalar dot with a vector gives you a vector. So from this we can come to the conclusion that the double integral of a scalar dot with ds equal to the triple integral of a scalar dot with nabla. And now we can say that the double integral of the pressure dot with ds is equal to the triple integral of the divergence of the pressure. And now recall that pressure is h rho g. Derivative of the pressure with respect to both x and y is equal to 0. And h here simply same as z. That all reduces to rho g k hat. And now we can move rho g k hat out of the integrand because they are constants, and the triple integral of dv is simply the volume of the object. And that all simplifies down to rho gv times k hat. And that is the solution. Because the z-axis is pointing in the downwards direction, the value of g is negative. And that tells us that the direction of the force vector is pointing in the upwards direction, which is opposite to the weight of the object, and the magnitude of that net force is equal to rho gv, where rho is the density of the fluid and v is the volume occupied by the object, and g is the good old gravitational acceleration.
What we should care about is not the total volume of the object, but the volume occupied by the object in the medium. When the upthrust is greater than the weight of the object floats, and when the upthrust is less than the weight of the object, then the object sinks.